All right, we should now be recording. So in terms of what you should currently be seeing on your screen, we have Section 8, line segment congruence stuff, to be very non-precise. So the things that we're going to talk about tonight with our line segment congruence information is specifically on how to verify your congruence axioms in whatever model you have. So last time we talked about that first congruence axiom where it was, in layman's terms, take any line segment you have in your geometry and copy it somewhere else. Okay? So we're going to start tonight with our second congruence axiom and see how that would work. So to remind ourselves, when we talked about the first congruence axiom last time, we used the double model. So I'm not going to use the double model tonight. I'm going to pick on two different models when we go ahead and look at these next two axioms. But to remind ourselves of the models we've been looking at specifically are R2 models. Any model on R2 has ordered pairs for the points where both coordinates of the ordered pairs are going to be real numbers. Anything we consider a line is simply a straight line, so no curves, no parabolas, no things that look like proper circles. Those aren't considered lines. The only thing we're going to consider lines with the geometry are straight lines. The A, B, and C are real numbers, so our coefficients are real numbers. Betweenness is defined exactly how you would hope it would have been defined. We have three different points. If B is the point between the other two, not only are the 3 points on a single line, but one, or at least one of these four inequalities is going to hold true. So if you have a vertical or a horizontal line, you'll have exactly one of the four inequalities holding true. If you have a non-vertical, non-horizontal line, you'll have exactly one from each of these bracketed inequalities to hold true. So one or the other, one or the other. Okay? And then we said in a model where congruence of line segments is defined, any two line segments are congruent exactly when their distance formula is the same. When I say that, we really mean what? Again, in layman's terms, this would be exactly the same thing as saying the length of the two line segments are the same, using whatever distance formula is actually associated with the model. So we had four models that we've been dealing with on R2. The first one is the standard model, and this is the one where the distance formula is you take the difference in x coordinates squared plus the square of the difference of y coordinates, and then you take the square root of the whole thing. I don't care if you remember the name, but this one actually has a name besides just standard model's distance formula. This is called Euclidean distance because it works the same way as how distance would work in the model that Euclid put together. Although technically he probably thinks of it more as the only geometry that existed, but anyway. We also had the taxicab model. So our taxicab model distance formula was the absolute value of the difference in x values plus the absolute value of the distance in y values. And we also had our soup model, which corresponded exactly to the maximum of the absolute value of x, difference of x values versus the absolute value of the difference of y values. And then the double model that we looked at last time is the piecewise function. So for distance, if your x and y coordinates, if one of the two of them are the same, so if both x coordinates of the 2 points are the same or both y coordinates of the 2 points are the same, your little line segment will look vertical or horizontal, and that in that case you would then use the same distance formula as the standard model. Okay? And in any other case, in other words, where both the x coordinates and the y coordinates are different, so the stuff inside the parentheses is non-zero in both situations right there. This is when you would double the standard model's distance formula or twice the Euclidean distance. Now, tonight we're not going to look at the double model, but we are going to look at these three models. We'll look at the standard model first, and then we'll also look at the taxicab model and the soup model, depending on how far we get with the examples. So let us move into an example. So the first example that I've got for us is wanting to verify that the second congruence axiom works in the standard model or is satisfied by the standard model or holds in the standard model. So just to remind ourselves, our second congruence axiom was if you've got some line segment AB congruent to some other line segment CD and AB is congruent to another line segment, those two line segments that AB is congruent to are themselves, of course, congruent. Now, the second congruence axiom also has a second part, and the second part of the second congruence axiom says every line segment is congruent to itself. In other words, this guy. So AB congruent to AB. Now, remember how line segments were defined to be congruent? It was by way of a distance formula. So in order to get that that's true, we would have to verify that the distance between A and B has to equal the distance between A and B. So what do you guys think? Is that formula with the distance functions in it true? Don't overthink it. What do you think? Is the distance from A to B equal to the distance from A to B? Yep, this is where if we were in class, hopefully all of you or most of you would be nodding your heads. So what you would say if you wanted to show that AB is congruent to AB, you'd say, hey, pick any 2 points. So pick any 2 points, A and B. And specifically, we don't want A and B to be equal to each other, but they actually could. We wouldn't have a line segment, but the formula here would work. And then you'd say, well, our distance formula is, of course, equal to each other because you're going to get real numbers. And that would mean, by definition, you get this guy. So I'm just going to go ahead and say, yep, it works just by that little outline. Note, that's not super formal because we still had all the arrows and it didn't go properly top of page to bottom of page. But this would be the idea of why every line segment is congruent to itself. So what I'll focus on instead right here is focusing on why C2, that second congruence axiom, is true in the standard model, or it holds in the standard model. Now remember, this is, in order for this guy to hold, you have to look at every situation where you have one line segment, which we call AB, congruent to two other line segments. And then you have to verify that in that case, you will always get your conclusion of CD congruent to EF. So what we're going to do is I'm going to put this into a proper T-chart format, mainly because we haven't done that much when we've been up in the Hilbert geometry, but it always works anytime you want to do a proof. So here's the setup. You grab your givens, and in this case, you actually have two pieces of information that are given. You have both AB is congruent to CD and AB congruent to EF. You could totally put them right here. I'm going to hold on for just a second and put that second piece of information in just a second. Instead, I'm going to reinterpret this idea of line segment AB congruent to line segment CD in terms of the distance function. So remember our definition of two line segments being congruent to each other in the model. That means we will automatically get that the distance of A to B, distance C to D are the same, or the lengths of two line segments are the same. So that's just the definition of how congruence for line segments is defined in our model. Then I'll go ahead and throw in the next piece of given, or next given information. And we only really had two pieces of given information, so this will be the last thing that will say given under reasons. And any guesses what I would do for step 4? Or I guess could do for step 4. There's typically more than one option. So what we're going to do is we're going to throw these guys into a distance formula as well. So what we're going to do is we're going to say, and I'm just going to reinterpret exactly what we had from statement 3. I'm not going to make it fancy right yet because be careful. This exact axiom is really, really easy to say, yes, of course it's true, and then not put in middle steps. So I'm going to be very careful about putting in the middle steps. So here we just interpreted what it meant to have two line segments to be congruent to each other. And step 5 that's about to throw in is probably one of the more important steps of this total process because it's going to make everything that you want to do actually work. So here's what I'm going to claim. I'm going to claim that the 3 different distances that we've calculated above step 5 or above statement 5, so that whatever the length it is from A to B, whatever the distance from C to D is, whatever the distance from E to F is, I'm going to claim that regardless of what line segments you have, those 3 values should all be real numbers. What do you guys think? Any guesses why those values, those distances should all be real numbers? don't overthink it. Well, there is that. Distance can't be imaginary. That's a good thought. So I'm going to throw us back to the formula for standard model distance. So we are looking at this guy right there. I really did not want to do that. There we go. Remember, all the x and y coordinates are real numbers. So you've got 2 real numbers subtracted, then squared, 2 real numbers subtracted, and then squared. So that means each of these components right there are going to be positive or at least not negative numbers. Yep, you add them together, you'll still get a positive or at least not negative number. And then you take the square root. And seeing as there's no negative out front, that means you always take the positive root. So if point A and B are 2 different points, not only do you get that they're real numbers, you actually get that they're what type of real numbers? Anybody have a guess? Yep, so they would be positive real numbers. Okay. Now, we're not going to need the positive real numbers part. All we're going to need is the real numbers part. So we've got that these guys are real numbers, and if you wanted to, you could say positive real numbers. And I don't remember if we've done this in this class. The symbol for positive real numbers is you put a little plus up where it looks like an exponent. All right, so I'm going to say that the reason for that is I typed in definition over here before class, but this here totally depends on the formula of your actual distance function. So that's where you have to go back and look at your distance function for your particular distance function in whatever model you're in. You go and you check, did I actually get back real numbers? And that's how you would verify. Now, after statement 5, we're going to use properties of real numbers. And that's why statement 5 was so important. So I'm going to claim the next thing, and you guys see if it looks believable. I'm going to claim that for statement 6, we have previously the distance from A to B was the same as the distance from C to D. That would be our statement 2. And I'm also going to claim that the distance from A to B equals the distance from E to F. Statement 4. And this is something that math people who are especially lazy like to do, which is string a bunch of equals together. So the question is, what do you think? Does that look like it's a believable thing that you can do? Remember, we're working with real numbers. So yep, it turns out that is totally something you can do if you're working with properties of real numbers. So something you already know. So then the next statement, I'm just going to clean up statement 6. So this guy here is just a rewriting of statement 6 without the middle step there. So I said, hey, the distance from CD is the same as the distance from E to F. Now this right here is where we're almost done. If you've got the distance of lines, the distance from C to D is equal to the distance from E to F, what does that really mean you have right now? Any guesses? So this is where you go back to your, yes. So this is where you go back to your definition of what it meant for line segments to be congruent. So this would tell you, hey, your 2 line segments, C to D and E to F, those 2 line segments are going to be congruent. And this definition right here on step 8, that one would be referring to your definition of how we've defined line segments being congruent to each other. Okay? And that's it. At that point, you're done. And I think I have a last fly in. Yep. So what that means is that this second congruence axiom would totally hold in this model. Now, here is the big question. Was there anything in this work that would be specific to the standard model and would not work in one of our other models on R2? Anybody have a guess if that's possible or the case? In other words, is this, are these steps, is this reasoning specific only to the standard model? What do you guys think? it would actually work for all 4 of our congruence models. So the big thing here, the first 2 pairs of information deal with simply anytime you have a model that has a distance formula, so you get those first 4 statements right there. Now, statement 5 is where everything starts happening. So everything after statement 5 is just dealing with properties of real numbers, and then we pull back definition of how line segments are dealing with. So if you have where your distance functions give back always real numbers, you can use this exact same proof, these exact same reasons in any model where your distance function gives back a real number answer. Let's look at our 4 models. If we're looking at these 4 models, we've got our standard model right here. We already said the standard model gave back a real number answer all the time. In fact, a positive real number answer. Now, taxicab model, I see several of you saying, yeah, you think it would work. Well, notice you subtract 2 real numbers, you'll still get a real number. Even if you didn't have the absolute values, it would still work. Down here with the soup model, again, you subtract 2 real numbers, you'll get 2 real numbers. Then you have to choose between 2 real numbers, and you'll have to get a real number. And then when you get down here to the double model, it's the exact same formula as the standard model. So if standard model worked, double model will definitely give you back a real number. Even if you're in this doubled up situation, what would happen? You would just twice whatever real number you would have gotten otherwise. So this procedure we just did will actually work for any model with, and here's the key thing, a distance function that will always give you back some real number. So if you have a distance function that for whatever reason is not giving you back a real number, first of all, issues, but second of all, you would have problems right here if you're trying to verify your second congruence axiom. Also, if you had a model that line segment congruence was not defined by way of a distance formula, you would also have to do this differently. For us, we're going to define line segment congruence by way of a distance function, so this sort of structure should work in pretty much any model we look at. Questions before we move on to the third congruence axiom? All right, I'm not seeing any questions from you guys, so I'm going to go ahead and move us on to our third congruence axiom. So third congruence axiom is a little bit different than what we talked about when we previously stated our third congruence axiom. It turns out the third congruence axiom can be rewritten if you have a distance function involved. So here, all you have to check to make sure that the third congruence axiom holds if you have a distance function is you pick any set of 3 points in your geometry where you have the relationship that point B is between points A and C. Then, for those 3 points, you have to check to see if that equation is true. So you haven't, what's a good way to phrase this? You would figure out what's the distance between point A and B, you'd figure out the distance between points B and C, you'd figure out the distance between points A and C, and then you check to see if you plug them into this formula, do you really get an equals right there, or are they not equals? Okay. All right, so let's see how the setup is. So here's what you would start with. In other words, your givens. So you'd say, hey, suppose we've got 3 points, and we know that if we want this condition where point B is between A and C, they're going to have to all be on one line, so let's go ahead and call that line, line L. Now, we've dealt with lines before. There are 3 cases for the orientation of the line, and it turns out things act a little bit differently depending on which orientation you're in. So, we'll need that in just a second. I forgot I was about to throw it in there. So we're also going to go ahead and assume that A has the smallest fill-in-the-blank coordinate. For 2 out of our 3 cases, it'll be the smallest x coordinate. For the first one, though, it's actually going to be the smallest y coordinate, so I'll cross that off when we get to our first case. Okay. So case 1 is going to be here that our line L that all 3 points are on is vertical. Now, if you have a vertical line, all of your x coordinates are the same, so it makes no sense for A to have the smallest x coordinate. It's automatic. So let me go ahead and draw a picture here. And I'm just going to put this line in the first quadrant to make my life easier. So here's A, here's B, here's C. Okay. And notice if you naturally had C to be the lowest of the 3 points, you can just relabel it so that the lowest point is point A. Okay. Now, here's the deal. You have to have point A, B, and C be arbitrary 3 points on this line, and the line L also has to be an arbitrary line. In other words, this has got to work for any vertical line, and it's got to work for any 3 points on your line. And then once you pick those 3 points of the line, the middle one is tagged as B, lowest one is A, and the highest one is C. So in order to replicate that in terms of your notation, I'm just going to go ahead and say that point A is given by A1, A2. Now, once you've decided that, what do you know about the x and y coordinates for point B? The x coordinate would be what? Any guesses? X coordinate of point B? Don't overthink it. Yes, it would be A1. We are a vertical line, so all of these x coordinates would actually be the same. They would not change. Now, here's the part where we need a little bit of extra information. Suppose that this distance between A and B right here, or that the change in y value between A and B right there, is given by an h. Pretend that squiggle was an h. Once you identify that the change in y would be h between the points A and B, what would that mean for the y coordinate of B? And it looks like several of you are already starting to write it. So you would just add h to the y coordinate of A, and that's it. You now have a formula for your point B. And notice, specifically, it's with this formula for B, you are guaranteeing that it is vertically on the same line as point A. And if you want to guarantee that point A and point B are different points over here to the side, you'd say something like, hey, h here has to be not equal to 0. I'll do positive because we went up. Okay? Now, if we look between point B and point C, we can do the same sort of thing. But here's the big question. Is there any guarantee that the change in y value from point B to point C is the same as the change in y value between point A and point B? Anybody? What do you guys think? So there's no guarantee that this difference between B and C has to still be h. There's no guarantee whatsoever. It's totally fine if it is, but it's also totally fine if it's not. So in those situations, what you do to indicate that with symbols is pick a different symbol than h. Now, we still need k here, and h and k are the standards. We still need k to not be 0. Why? Because if k equals 0, point B and point C are the same point. And since we already went ahead and said, let's let A have the smallest y value, the k and the h both have to be positive to go up. Which means, what should be our formula for the y coordinate of C? So we'd take the y coordinate of B, so A2 plus h, and then plus that extra k. And there's your 3 formulas for, or 3 expressions, 3 representations for the for your 3 points. So I'm going to make a squiggle line here to indicate that normally I would probably put it lower on the page if I had a full page, but we'll just put it to the side here. What would we actually do in terms of trying to show that our formula is true? So here's our formula right up here. It's standard practice, although not always, doesn't always work this way, but most of the time when you're trying to show that an equation is true, you start with the more complicated side. So I'm going to go ahead and start with the distance from A to B plus the distance from B to C. Anybody got what the distance from point A to point B would equal? So this first distance right here should be the same as what according to our picture? Anybody got it? So this one here would be h, this change right here, or we would just subtract these y coordinates and get an h. Remember, we're soup model. Soup model says you subtract the y coordinates, you subtract the x coordinates, you get the bigger of the two values. In this case, 0 versus positive h. Let's go with positive h. Now, using the same logic, what's the difference, the distance, excuse me, between b and c? Hopefully you are all thinking distance between b and c is exactly k. So that would be k. And then the last thing we need to check, oh, it looks like there's a little bit of a lag when your answers come through. So yes, you are all right, k's. Now, if we want to go ahead and see if that actually equals the distance between points A and C, we just go over to point A, we go up to point C, and what would be the difference? What would be the distance from A to C in this case? Would it actually be the h plus k? What do you think? Is h plus k the distance between A and C? It is. So I'm going to go ahead and finish our formula right here, or our little string of equations, and say, hey, yep, we totally got the distance between A and C. And that would tell you, our conclusion right here would be that C3 holds in the soup model. Okay? Questions? Make sense? Kind of feeling okay? I don't see any freakouts yet. That's one of the nice things about when you do the different cases with lines. You have your vertical and horizontal and slanted lines. The vertical and horizontal lines are typically the easier two cases, so I would always recommend starting with them. That way you get sort of an idea of what you're doing and it's not complicated yet. Then move on to the main one, which is, in our case, going to be a case 3, where we have the slanted lines. And it'll be slightly more complicated than what we just did, but it'll follow the exact same pattern. All right, so let's move on to case 2. Case 2 is where we have a line that is horizontal. And in terms of the picture, it would look like this. So we've got some horizontal line. We're going to let point A have the smallest coordinate that changes, so the smallest x coordinate. There's where the x actually is true. Then we'll have our point B, and then we'll have our point C. And I'm not actually going to run down this full case 2. I'll let you guys fill in the details on your own. But quick check, would this case work the same way that case 1 would work? That case 1 did work, excuse me. Yep, it does. It works exactly the same way as case 1. There's exactly one difference. Anybody have a guess of what that one difference would be? Oh? Yeah, basically. So the one difference would be is, in this case, all of your y coordinates would be fixed. They'd stay the same. And your x coordinate would be where you'd add the little bit each time. And here, let me go back for just a second. So in terms of our formulas, right here, all of this plus h and plus h plus k would just be right over there in the x coordinates, and it'll turn out that this formula, when we start actually plugging it into the expression we wanted, that'll turn out to be exactly the same. All right, so that's all I'm going to do with the horizontal part, to say same as case 1, or I really should say similar. Similar to case 1. All right, so let's get to the third and the last case for Congruence axiom number 3, and that is what happens if your line is slanted. So I went ahead and threw up all the information that we need. Remind ourselves of what's going on with our third congruence axiom. We're going to start off with 3 points on one line. Point B is the one between the other two. And then we're going to try to get to that boxed formula. We're starting off with 3 points on the line. We're assuming that they have that betweenness relation. And we're also assuming that our line has the format of y equals mx plus b, where our slope is not 0. Technically speaking, everything we do here in case 3 would work if the slope is 0, and you could merge case 2 and case 3 together. That was not the main reason I skipped case 2. It was mainly because we'd literally just done all the work, but that is something you could have done to also skip case 2 if you wanted to. All right, so let's see what happens. And this one, I believe I've got fully typed up here. So first thing is the picture. So I've got a slanted line right here. In this particular case, I went ahead and put a positive slope line. You can totally do the exact same thing with a negative slope line. It'll act the exact same way. So I'm just going to focus on the positive slope line. So first thing is we'll go ahead and we will assume that our x has the, not x, our point A has the smallest x coordinate, that same assumption that we had back in case 2. And we say, hey, you know what, I don't know what A is, but I can go ahead and give it a formula. So then we say, now that we know what A is, we need to figure out what B is. And just like before, both points B and point C are going to be able to have a format or an expression in their x and their y coordinates that is built specifically from point A. And you need that to guarantee they're on that same line L. So here's what's different. Both point B and point C, their x and their y values, or x and y coordinates, are going to change from the x and y coordinates of point A. So we're going to add something to both of those two coordinates. So here's how to find it. So here we've got that our change in x, we're going to go ahead and assume is h. You can totally assume your h here is positive. It can't be 0 because if h equals 0, the 2 points A and B would be the same point. You could technically make it negative if you want to, or if you want h to indicate the distance, you could go ahead and keep it positive, and then if B was really on the other side of A, you could say, hey, subtract h. There's options. But we went ahead and assumed that x had the smallest x coordinate, so we can definitely say that h here is positive. Now, this guy right here, m times h, this would represent the change in y from point A to point B. And I'm pretty sure we've done this before, but to remind ourselves, remember slope is given by the formula change in y over change in x. So if you want the change in y, that is simply slope times the change in x. And we have that our change in x is h. So that would be how we got the formula h times m, or as I wrote it down, m times h. Now, what does that mean for us in terms of point B? What would you need to add to the x coordinate of A to get the x coordinate of B? What would you need to add to the y coordinate of A to get the y coordinate of B? Well, it would be the two things we just found on those legs of that little right triangle and the dotted red line. It should be that guy. Huh? Notice in this orientation right here, if you did have a negative sloped line, right here, if this was A and this was B, you could still say that that part's H. This drop then, in other words, you want the y value of B to be smaller. The H is still positive, but now the M, being negative with a negative slope, would actually subtract from your y coordinate of A, and that's why it works out just fine. So this, what we've done here will work both with positive and negative slope lines. All right, so next thing we need to do is go ahead and calculate the format for point C. And just like when we were on the vertical line, there is nothing that says the change in the x coordinates of B to C, it has to be the same as the change in the x coordinates of A to B. So you need to make sure you pick a different letter. And I went ahead and down here at the bottom remarked that, hey, we're assuming here our K is positive. And using the same format as before, using the slope of the line, we could calculate the change in y. So same deal, we'll go ahead and we'll add those two values or those two symbols to our x and our y coordinates of point B. Make sure you add it to the right side. I should say side, right coordinate. Okay. So C then would be you add the extra k to the x coordinate and you'd add the extra k times m to the y coordinate. All right. So that gets us our formats or our expressions for the 3 points. Any questions so far? Everybody okay so far? All right, so that takes care of all the nitty-gritty details in terms of where the actual, I shouldn't say the actual work of the problem, but this setup is the part that takes the most thinking. It's probably one of the most important parts of getting to answering this question, just because if you don't have the setup right, everything else is going to be difficult. Okay. So we do want to go ahead and show that our equation works. So what we want to do is next, we're just going to calculate the distance between A and B, the distance between B and C, the distance between A and C, and then check to see if it actually works if you plug it into the equation. Okay. So first thing I've got here for us is distance from A to B. So looking at point A and point B. And remember, our soup model is you're looking at the maximum of the change in x's versus the change in y's. So change in x, we have the h. Change in y, we have the h times m. And remember, you really put everything inside of absolute values. H is positive, so the absolute values don't matter. So I didn't bother to put them there, although it's totally proper to go ahead and put in the absolute values. But m could be positive or negative, so you cannot drop the absolute values off of the m. Now, technically speaking, this guy is a piecewise function, and I would definitely write down what I'm currently about to write on this slide, because it is going to disappear as soon as the next formula comes in, and we're going to need it here in just a second. A maximum is technically a piecewise function. So there's two options for your answer. It can either be h or h times the absolute value of m. Any guesses when you would get h? Ooh, I have lots of answers. Excellent. So whether you get one of those two guys or the other, yes, totally depends on the value of m. So remember, h is positive. The absolute value of m is also positive. So we're actually going to look at the absolute value of m. If you're only dealing with a positive slope line, you don't have to worry about the absolute value or not. So in our picture, it doesn't matter because it's just a positive m. But if this was negative, you'd have to make sure to take the absolute value of your slope. Now, if you compare these two guys, think of your h as like, I don't know, a 2. So if you've got 2 versus 2 times the absolute value of m, when would 2 times the absolute value of m be bigger? Yes, you compare it to 1. So if the absolute value of m is bigger than 1 or smaller than 1, what happens? When is h the bigger one? When absolute value of m is bigger or smaller than 1? I see all of these. Oh, I've got a couple of extra votes from you guys. Okay. It turns out when the absolute value of m is smaller than 1. In other words, slopes between negative and positive 1. That will then shrink whatever h is. Then if you actually want something bigger than h, that'll happen in terms of positive numbers if the absolute value of m is bigger than 1. And what would happen if the absolute value of m actually equals 1? So the slope is either positive or negative 1. Would it matter which of those two pieces of your piecewise function you used if your absolute value of m equaled 1? Correct. It would not matter, because if the absolute value of m equals 1, down here in this second expression, you'd have 1 times h, which is the same as h. So you could pick either one you want. So if you write out this piecewise function, you pick whichever piece you want to put the equals on. That way you actually know what happens when m equals 1 or negative 1. Got to be somewhere. And standards, people really get fussy if you put the equals on both of the two pieces. So I'll not do that. Okay. All right, so next thing we want to calculate is the distance between B and C. As soon as I push the button to pull that one in, everything we just wrote is going to disappear. Seeing nobody fussing at me and saying, wait, I'm going to go for it. All right, so distance between B and C is going to be the same idea. So point B to point C. The only thing we added on was the K and the K times M. You take the absolute value of both. Absolute value of K, since K is positive, doesn't change. Absolute value of M might change if you'd have what? If you have a negative value for your slope. Just like with what we did, this is technically a piecewise function. You get back either K or K times M. And if you were trying to write down the domain of each of these pieces in the piecewise function, it would still be off of the absolute value of M. And it would actually be the exact same split. Pretend that was actually in an inequality and it didn't curve on me. It's actually really key here that the domain of this piecewise function is split at the same point at absolute value of M equaling 1. What that means is you are totally able to add these two pieces together correspondingly straight down. So these two pieces would be added together and those two pieces would be added together if you needed to add those two distances. Okay? So that would mean that the sum, and I'm just going to write sum because I'm lazy, would totally equal H plus K, and then technically here, H absolute value of M plus K absolute value of M. Okay? Questions make sense? Kind of okay so far. Doesn't look like there's anybody with a question yet. If that changes, definitely flag me down either via the chat or some sort of creative symbol over if you're doing the symbols that you guys can select. All right. So the next thing we want to do is we want to go ahead and figure out what the distance is between A and C and compare it to that. Now, since what we just wrote in terms of the sum of those two distances is in blue, it's about to disappear as soon as we go to the next thing. So I am going to claim that the distance between A and C is that same expression that we found from our sum. So the easy one to see is if when we're going from A to C, the change in X is definitely just the stuff we added on to A1. Now, this second coordinate actually had a little bit of algebra done to it. Technically speaking, the change in Y coordinates is the absolute value of H times M plus K times M. And you can factor out an M. This is the same as H plus K times M. Remember, H plus K is positive, but M doesn't have to be positive, so you keep the absolute values around the M. That format was just multiplied out. Now, conclusion. What does that tell us about this third congruence axiom? Does it hold in the soup model? What do you guys think? Should we say, yes, our congruence axiom holds? Or no would be, you think, no, it doesn't hold. Well, I have one response. Anybody else have a guess before I say what the right answer is? Ooh, I've got people doing check marks. Ooh, more yeses coming in. Awesome. More check marks. I'm actually impressed. I thought I was going to get some emojis. All right, so it turns out, yes, what did we get? Since our sum equaled exactly the same expression as the distance from A to C, even though I didn't put all of the algebra in the actual typed work here, what this does mean is, yes, congruence axiom number 3 does in fact hold in our soup model. I believe that's going to fly in right here. So that would be our conclusion is, yes, it works. And that's it in terms of your congruence models. On Monday, we talked about the first congruence axiom and then when it worked, when it didn't. Here, I just showed you 2 examples of when it works. The only last thing that I've got for us in terms of section 8 for tonight is looking at the triangle inequality. But in terms of congruence axioms, literally the same exact format that we covered on Monday and tonight is what you would do if you needed to verify a congruence axiom works. Or, like the example that we worked on in an activity on Monday, that would be what would happen if the congruence axiom doesn't work in your model. Questions before we move on to looking at the triangle inequality? There should have been a question mark at the end of that sentence. All right, I don't see any questions from you guys, so I'm going to go ahead and take us on to what the triangle inequality is. So the triangle inequality was totally known by Euclid. It's actually in Euclid's Elements. It's in book 1. I believe it's proposition 20. I forgot to check the number before our virtual class tonight. I'm pretty sure it's 20, but if not, it's really close to 20. Okay? So remember, our standard model on R2 totally mimics the geometry that Euclid put together. And once we get all of our congruence axioms that we need, we're actually going to exactly reproduce the geometry that Euclid put together. So because Euclid already talked about why the triangle inequality does work, I'm going to skip out on talking about standard model. Instead, I'm going to focus on what this would mean in a different model. Okay? So first thing is, this says you start off with any 3 distinct points. There's 2 situations. One of those situations is where the 3 points are not on the same line, so you actually get a triangle. And the other situation is where those 3 points are on the same line, and you just get a line. Okay? So we're going to break it up into 2 cases. We'll look at all 3 points on a line first, and then we'll look at what happens if they actually form a triangle second. And notice the name of this guy, the triangle inequality. Most of the time when people think about the triangle inequality, they are thinking of that situation where you actually form a proper triangle. But both of these cases technically will work. All right, so the claim is the triangle inequality will always work for any 3 different points. However, here specifically for collinear points. Okay? First case is, suppose your point B is actually between the other 2 points. And in that situation, let me go ahead and draw in a picture. So here's our 3 points. There's A, there's B, and there's C. And if you apply the third congruence axiom that we literally just talked about, it says add up line segment AB, or if you look at line segment AB, you then look at line segment BC, you add them together, that should totally be congruent to line segment AC. And remember, in terms of a model that has a distance formula, this expression with the congruence is exactly the same thing as writing the length of AB plus the length of BC is equal to the length of AC. That was trying to be an A. Huh? And that's exactly what your third congruence axiom says. So bam, we're done already with that part. Only situation is, this is not the only orientation of your 3 points. Any guesses of another way that we could rearrange our 3 points A, B, and C on a line? Anybody got a guess? So that would be one of them. So the guess was put point A in the middle. Unfortunately, that's not the one I typed up. I actually did it alphabetical. So the other case that we have is where point B is not the point in the middle. So I wish I could have automatically come up with the one you suggested, but it turns out you can have either A or C to be the point between the other 2, and it'll work exactly the same way. So if we go ahead and look at the third congruence axiom again, so here's A, here's C, here's B. By that third congruence axiom, we have that AC plus BC is going to be congruent to the entire line segment AB. Now, what does that mean for us in terms of AC? Well, if AC plus something has to equal AB, that actually tells you that AC is shorter than line segment AB. Now, if line segment AC is shorter than line segment AB, and the only thing you were trying to show was to go ahead that line segment AC was shorter than AB plus BC, do we automatically have the inequality that we want? Yes, I see your inequality question. I will get back to that in just a second. So assuming that we have AC is shorter than AB, will we automatically get that AC is shorter than the sum of line segments AB plus BC? What do you guys think? Does that implication look true regardless of whether you believe the first inequality? And the reason that that would be true is if you already have the inequality and you add something longer, you make the line segment AB longer, out here maybe, of course you're still going to have the same inequality. Now, to go back to the question, how did we get that AC is shorter than AB? Oh dear. Oh, they all came in at once. So definition of AC being shorter than AB is the shorter line segment and the longer line segment. If they share a point, so here's them sharing the point A, shorter line segment has a point that is in the middle, or it is between the endpoints of the longer line segment. And that is just the definition of two line segments being, one being shorter than the other one. So if we draw this with getting rid of the writing there for just a second, suppose you have AC. And then if you have to extend this line out to get here to B, notice the key things you have. You have your C is between point A and B. Then by definition, you've got somebody who's only so long and somebody who's longer still. Okay. So that would be inequalities of line segments. Just as a heads up, to be fair, it was a while ago, but I posted a couple of little short videos on Canvas that talk about some of the definitions we skipped over in class. One of them is line segment inequalities. And I definitely drew the picture much better than that scribbles right there. So if that helps, go check out that little snippet of a video on Canvas. It's linked under the section dealing with congruence. All right, so that deals with what happens if the 3 points are all on the same line. Let's look to see what would happen if your 3 points are not all on the same line. Okay? I put some background here up top, and the background is we're going to go ahead and assume that our line segment AC is the longest, because if it's not, you get the inequality immediately. The first case is, okay, well, we've got this longer line segment AC, and then we've got the two shorter line segments AB and BC, and on purpose, they are vertical and horizontal lines. Now, the other thing to remember is, this example is in the taxi cab model. So taxi cab model is, if you form a little right triangle, the distance between your 2 points is the sum of the length of the two legs. So notice what happens here. The length of AC is the same as the sum of the distances of the lengths of A to B and B to C, which means you actually get an equality. That's okay, because our inequality included the congruence right there. Now, here are the rest of the cases. So the rest of the cases you could have is what if you don't have two of your sides being one vertical and one horizontal. And in these are the only three situations you can have. The only way it'll change is if the pictures rotate. So here you've got your longest side. AC is a diagonal of that dotted rectangle. This dotted rectangle is formed by the change in X, change in Y's needed to go ahead and calculate the distance using taxicab method. And I did that for all of these guys, all the way down. Now, if you look at all of those pictures, notice what's the same for all of them. If you add the total distance of A to B, B to C, A to C, so A to B, B to C, and A to C, and you do that for any of those three situations, you'll get the total perimeter of that red rectangle. Now, if you only look at AC, notice its distance is going to be the length of one line segment, possibly a second line segment, possibly part of a second line segment, or possibly just that one line segment, which means in terms of the percentage of the perimeter of the rectangle, at most, you are going to get up to half the perimeter, which means from that first comment we did, the sum of the other two sides of your triangle has to make up the rest of the perimeter. So the other half or more than half. Since it could be more than half, that's where you get this inequality. And once you have that inequality, you're going to automatically get the inequality on the line segments as well.